So thanks very much for the invitation. This is the last talk of the conference. So before I go any further, we should really have a big round of applause for the organizers who have put together, I think, a great conference in what must have been really tricky situations. So it's really nice to see actual people at an actual physical conference, even if I'm not there. So thanks very much. Okay, and so I'd like to talk about the knot-Floer homology of knots in the solid torus. And this is an extension of some earlier work that I did with Liam Watson and Jonathan Hanselman. And in fact, really, I mean, there are in some sense no new ideas. It's just a matter of taking this particular problem and inserting it into the machine and turning the crank. But I think that it's interesting to understand what the answer is. Especially because there's been a lot of progress in understanding various forms of other categorified homologies for knots in the solid torus or knots in the annulus times I over the last 5 years. I think it's nice to know what the answer is here. Okay, so let's just first talk with, start with a little bit of a general picture. So the story that we all know is that if I have a manifold with boundary with some knot inside of it like this, then there should be some sort of vector space associated to the boundary, and that knot should define some element in the vector space. And when we categorify, we expect to get a category associated to the boundary and some sort of object in that category associated to the knot inside. And now, so for example, if I glue two things together along this boundary, I should take the pairing in the sense of Homs between objects in the category. And so that's the general philosophical picture. The particular example that I want to consider in the decategorified sense corresponds to the multivariable Alexander polynomial. And already we see that, the picture is maybe a little bit more complicated than just that. All right, because the natural vector space associated to this boundary torus for the solid torus is actually the group ring of the homology of the boundary. Okay, whereas the invariant lives in a somewhat different group ring. It lives in the group ring of the homology of the knot complement. Okay, and so effectively what that means is that we see that the theory kind of breaks into sectors, analogous to what we saw in Sergei's talk. And those sectors correspond to elements of the co-kernel of the map from H1 of the boundary, and this should be H1 of M minus K. And actually, just as in Sergei's talk, those elements correspond to spin C structures in some sense. Okay, so now the kind of categorification that I'm interested in thinking about comes from the Heegard-Floer homology of Oshvat and Szabo. Okay, and in Heegard-Floer homology, there are two ways that we can think about the boundary of a manifold, three manifold with boundary. Okay, so maybe, for example, I have this manifold here, which is the complement of the trefoil in S3. Okay. So the first thing that I can do is I can suture this boundary, okay, and consider the sutured Floer homology. So in this case, this amounts to choosing a pair of parallel curves on the torus boundary, and that those curves split the boundary into a top half and a bottom half, which maybe I'll color red and blue. Okay, and so the separation between the top and the bottom is the suture, gamma M. And if we choose the meridional suture, the one with which, if we fill in, we just get S3 back, then this sutured Floer homology is just the knot-Floer homology. Okay, so we get out of this picture a bigraded group, and a pair of differentials on it going to HF hat of S3, which is just the integers. And that operation corresponds to Dane filling along the meridian. Okay, so for example, for the trefoil, as you probably all know, we get these three groups and blue differentials and red differentials is shown. Okay, and so I should have mentioned that sutured Floer homology is due to Uhas. Okay. All right, so another thing that we can do with this boundary is we can consider it as a bordered manifold in the sense of Lipschitz, Ojvath, and Thurston. Okay, and so maybe I should emphasize that this sutured boundary is non-gluable. When I see a manifold with sutures, I can't glue it to anything else. Okay, whereas the whole point of the bordered boundary is, the bordered theory is that it's set up to glue the bordered boundary to another boundary. Okay, and one thing that's important to understand about this theory is that if we zoom in here, you'll see that actually, even on this bordered boundary, we have to have a little tiny sutured disk that really is sutured in the sense that we can't glue it. Okay. So what else should I say about bordered Floer homology? Well, just like Ina, using bordered Floer homology, we have to work over the field with Z mod 2 coefficients. Okay, is currently not a theory with integer coefficients. That's probably more due to a lack of sufficiently compelling applications to force someone to write down the theory than any obstruction to doing it. And so in general, this bordered Floer homology is fairly complicated to explain, but in the case when the boundary is a torus, it's not so hard to understand. So what Lipschitz, Ojvath, and Thurston tell you is that to this manifold with torus boundary, I get something they call a type D structure, okay, over an algebra associated to the torus, okay? And in general, this would actually be a DGA for a general surface, but here it's just an algebra. And it's a very simple algebra. You start with the quiver algebra with a pair of idempotents, which are black and white, and then these three morphisms, row 1, row 2, and row 3 between them. Then we divide out by these quadratic relations. So this is not a very complicated thing in some sense. And so in this sense, what's the invariant of the complement of the solid torus? Well, it's a chain complex over this algebra, a twisted chain complex. There's not a natural homological grading on it, but we have generators, which are shown by these copies of the idempotents, and then morphisms between them, which are shown by these arrows, and d squared equals 0 in a suitable sense. Okay. So in this case, when the boundary is a torus, this bordered Floer homology story has a nice graphical interpretation, which Jonathan and Liam and I described. And so what is this interpretation? Oops, shown too much. Okay. So what is this interpretation? Well, what it does is it takes CFD hat of M, which is this chain complex over this algebra, and turns it into some data, which is a collection of immersed closed curves, possibly equipped with some local systems, in a covering space of the punctured torus, which you should think of as being naturally identified as this, the boundary of the manifold minus that little sutured region. Okay. So for example, if we have the complement of the trefoil, then we get a curve in a covering space of the punctured torus, which is actually this infinite cylinder obtained by taking this strip and gluing the ends together. And the curve just looks, oops, like this. Okay. Okay, so where does this picture come from? It didn't come out of, well, nowhere. So traces back to an idea of Aru and Lakili and Perutz, which says that if you give me a type D structure over a manifold with boundary of any genus, not just a torus, then that should give you an object of the Fukaya category of the G-symmetric product of that boundary. Okay. And in general, there's no better way to describe the Fukaya category than just to do what Lipschitz, Ojvov, and Thurston did. But for the torus, you'd think that, well, Lagrangians in the torus are supposed to be curves, and maybe we could draw those. And in fact, there's a structure theorem, okay, which Hayden, Kontsevich, and Katsarkov proved, which is basically an algebraic theorem about chain complexes over an algebra like this, that says that you can actually break them up into direct sums of things that correspond to loops like this. So here you notice that every object has a pair of differentials coming out of it and chains, which look like this, except they stop at some point, so they don't close up. Okay. And in fact, somehow, we discovered this picture here and then realized that Hayden, Kontsevich, and Katsarkov had proved this theorem. And then we were able to give kind of a graphical calculus for how you actually turn an arbitrary chain complex over the algebra of the torus into a collection of loops and curves. And that's really something that Jonathan invented. So it's maybe useful to understand kind of what the correspondence is and what this graphical interpretation means. So let me say that, how does this work? Well, we pick this parametrization here, which I've sort of shown by these blue and red arcs. Okay. And the idea is that those form sort of a pair of generating one handles for a handle decomposition of the torus. And then I look at the intersections of those arcs with a curve, and those correspond to the generators that I see in this chain complex over here. So for example, here I see 3 black intersections, and there are these 3 black generators over here. And similarly, there are 4 white intersections and 4 generators here. And then the differentials, the arrows in this thing, basically correspond to looking for little holomorphic disks here. And here the secret is that you number these regions 1, 2, 3, and well, this is secretly 4, but maybe it's 0 and it never shows up. Okay, so for example, this region labeled 3 here in the diagram actually corresponds, I think, to this arrow right here. Okay. Okay, and the nice thing about this interpretation is that it's really easy to compute what the pairing between objects is, because really it's just given by intersections between curves after you've pulled them tight in a reasonable sense. Okay, so for example, if I want to compute the not Floer homology of the trefoil, I can get that by pairing with a set of curves that look like those vertical blue curves that we had before. Okay, and these 3 intersection points here, oops, it's not an intersection point, here, here, and here, correspond to the 3 generators of the not Floer group. Okay, and similarly here, maybe this red disk here is telling you about this red differential. Okay. Another thing we can do is we can Dane fill. So we can take this complement of the knot and just fill in a solid torus. Okay, and that corresponds to pairing with the invariant of the solid torus, which turns out just to be kind of a straight line in here. Okay, so for example, if I were to do -1 surgery, I would pair with this line of slope -1 in here, and I'd find that there were 3 intersection points. Okay, the -1 surgery on the trefoil gives me the Brieskorn sphere sigma 237. And here I see that there are 3 generators for the homology of this Brieskorn sphere. And I can even tell, for example, their mod 2 grading and homology just by looking at the sign of intersection. So for example, here there are 2 generators in one grading. Maybe I'll just draw dots here. 2 generators in one grading and 1 generator at this middle one and the opposite Z mod 2 grading. Okay, so each of these dots means a copy of Z mod 2. And you'll notice that back here I already forgot and wrote the wrong thing. I should have written F here instead of Z. Okay. Similarly, another thing I can do is I can think about the dual knot in that Dane filling. So that's the core of the solid torus I filled in. If I wanted to compute the knot Floer homology of that knot, instead I'd pair with this Lagrangian of slope like this. Okay, and so there are 3 copies of this Lagrangian. Those 3 copies are telling me about the Alexander grading in the knot Floer homology. So I see these 5 intersection points here. And that tells me that there's sort of 1 generator here, 1 generator here, and then 3 generators in the middle grading of knot Floer homology. Okay, are there any questions before I go on? All right, so then now let's think about the situation we're actually interested in, which is when we have a knot inside the solid torus. Okay, so what I'll do, I'll take the complement of that knot. So I have this thing over here, and I want to be able to glue and do things on the outer solid torus, but on the inner solid torus, I just want to think about it as a knot, okay, not something that I can glue along. And so what that means is that the inner boundary here should be sutured. Okay, so this boundary should be sutured, but on the other hand, the outer boundary I should treat as bordered. Okay. And now at this point, there are actually 2 different things, reasonable things that I could do. Okay, one thing is that I could actually join up the bordered boundary and the sutured boundary. So here's the bordered boundary on the outside and the sutured boundary on the inside. And I could join them up by a little tube. Okay, and to do that, I would have to pick an arc in the solid torus joining the inner boundary to the outer boundary. Another thing that I could do, which is maybe more natural, is I could just put a little suture disc on the outside, okay, and not join them up. And both of these are reasonable things to do. They were both studied in this context by Lipschitz, Oshva, Thurston under the name of bordered Floer bimodules. Okay, and so these 2 different things give me 2 slightly different objects. So if I do this thing where I use the arc, joining the 2 things in the tube, then I get something that I'll call little HFK. Okay, because it's smaller than the other option. And I'll get basically a non-compact set of Lagrangians. So in addition to closed loops, I'll get arcs. But there's, looks like there's a choice involved, right? I had to pick that arc. Okay, whereas over here, this looks maybe better. I'll get a compact object. There are no choices to be made. Okay, but if I glue, say I take this manifold and glue it to the complement of the trefoil, for example, which I might want to do if I were computing the not Floer homology of the cable of the trefoil, then what I'll see is that on this small side, actually the dependence on the arc completely vanishes. Okay, and that's because, well, if I glue in a little, so I have to remember sutured boundaries never glue. Okay, so I don't glue the sutured boundaries together. If I have a little sutured disc on this side, and I glue that in, well, that just kind of caps off this tube, and then it retracts back down to the inner boundary, and it doesn't matter which path I picked. Okay. Whereas over here, maybe things aren't quite so nice, right? So here, if I glue to do the same operation, I'll find that I pick up a sort of extra factor of the homology of S1 in the homology that I'm computing. Okay, and that's again because if I glue in this little sutured region on the other side, what I'll create here is I'll create a little bubble, a little hole in the manifold with a single suture on it. Okay, and every time I have kind of an extra one of those, it multiplies the homology by H star of S1. Okay. So for example, for the very simplest manifold that we could consider, okay, which is just, say I take this knot in the solid torus, okay, then little hfk turns out just to be given by this arc here, okay, whereas big hfk is given by this figure 8. And you'll notice that if I pair these two things with any other compact object, that's what a sort of manifold with boundary suture, sutured region is a little disk will give me. So maybe I paired with this compact object. Okay, you'll see that the homology on the right is twice as big as the homology on the left. Okay, so let's talk a little bit about spin C structures. Okay, so common feature in Heegaard-Floer homology. So I'll write for little hfk, but it's also true for big hfk. Okay, so this little hfk hat, this collection of curves, naturally splits up into a direct sum over the some set of spin C structures. Oops. Okay, and what is that set of spin C structures? So it's exactly the same co-kernel of the map of H1 of the boundary into H1 of the knot complement that we saw in the first slide. Okay, and so if the kind of winding number of my knot inside the solid torus is n, then that set of spin C structures is naturally identified with Z mod n. Okay. So that's one feature that it's important to understand. Another feature is the fact that, so I said back at the beginning, right, this invariant naturally lives in the Fukaya category of a cover of the punctured torus, not just in the punctured torus itself. Okay, and how do I decide what cover I'm taking? Well, what I have to do is I have to look at the map from pi1 of the boundary to, well, h1 of the boundary, and then into h1 of m. And I look at the kernel of that map. Okay, and that's the same as pi1 of the torus part coming from a puncture. So the part of pi1 of the cover coming from the torus. So in other words, ignoring the puncture. Okay, so here, for example, if the winding number is non-zero, then actually this map is injective. Okay, and we just get the cover which unwraps the torus onto the plane, and we get a lattice of punctures. Okay, and that's the picture that I was drawing back here. That's that lattice of punctures. Okay. So we need to choose coordinates on that lattice of punctures. punctures. Okay. And so there's a natural way to do that, which is to choose, I'll call them M1 and L1. Those are the meridian and longitude of this curve A in here, which is the braid axis. Okay. And so let's notice, oops, this should be L1 is 2M2. Okay. So M2 is the meridian for the knot itself. And that's just the fact that the winding number of this particular knot is 2. Okay. So since the winding number is 2, we get 2 different spin C structures. Okay, now we can ask, what is, maybe I'll draw HFK hat. So in one spin C structure, we get an arc like this. And in the other spin C structure, we get an arc like this. Okay. And if we were to thicken this up and work with big HFK, then we would just get figure 8s instead of arcs. Okay, so that's the knot Floer homology of this knot in the solid torus. Okay, so here I guess I've just drawn this again. Looks like this. Okay, so maybe let me discuss, actually maybe let me ask if there are any questions before I move on.
Sorry for interrupting. I was a little bit lost in my category. So are you saying that you get a different curve for every spin C structure?
Yes, that's right. Or a different, not, you know, here I happen to get a different single curve, but I might in fact get many individual curves in each spin C structure. But yes, these spin C structures are different. That's an important point to understand. And so, for example, one way to think about it is there's kind of a natural Alexander grading in this picture. And on one of these spin C structures, the Alexander grading is odd. And in the other one, the Alexander grading is even. Okay. Does that answer your question?
Yes.
Okay. Okay, so maybe any other questions? Maybe the most familiar property of any knot homology in some sense is you take its Euler characteristic and you get back, you know, the knot invariant you started with, right? So here we should take the Euler characteristic of these invariants and we should get back something to do with the multivariable Alexander polynomial. And indeed, that's true. Okay, so how do I take the Euler characteristic? It amounts to taking the homology class given by the boundary of little HFK hat, or alternately, the homology class itself of big HFK hat. Okay, and that naturally gives me not the multivariable Alexander polynomial by itself, but with this factor of 1 minus M2. Okay, and that factor of 1 minus M2 is the factor that always shows up when you suture a bit of torus boundary. Always multiply by 1 minus the homology class of the suture. Okay. So for example, here, for this knot we were looking at before, the multivariable Alexander polynomial of this knot is just 1 plus M1, M2. So it's got sort of 2 terms, which I'll mark by these 2 dots. When I multiply, I get 4 terms, okay? And how do those 4 terms correspond to this picture over here? Well, let me say that these 2 terms in the middle correspond to this spin C structure, okay? And you see here, this curve is linking this, this puncture here and this puncture here. That corresponds to these 2 generators. And it comes with sort of opposite winding number. That's the fact that these 2 things have opposite sign. Okay, whereas over here, these 2 loops here and here correspond to this and this. Okay, so I think the Euler characteristic is the most important property I want to talk about, but it's nice also to know that, like all Hegardt-Floer homologies, there's a conjugation symmetry. Okay, in this case, both of these spin C structures are spin structures. So they're fixed by the conjugation symmetry, but in general, that won't happen. They'll be permuted by the conjugation symmetry by an involution. And on each of these spin structures, there's a symmetry, which you can see here is sort of like this and like this. If you think about it, that's the conjugation symmetry that we get on this picture over here. Okay. And just like with a picture for the complement of the knot, where we computed things like Dane filling or the knot Floer homology of the knot itself, we can use this picture to compute a lot of things related to this knot in the solid torus. Okay, so for example, we can compute the Link Floer homology of this link. We can compute the knot Floer homology of the knot by itself. We can compute very naturally the effect of Dane twists. We can take satellites where this knot in the solid torus is the pattern. Okay, so maybe let me just illustrate the way those computations work. Okay, so for example, say I want to compute the Link Floer homology of this link. Well, what do? I pair with those same blue Lagrangians I was considering earlier. So here, and every intersection point here is going to give me a generator of Link Floer homology. And the position of the intersection points is going to tell me the kind of Alexander grading on the Link Floer homology. So for example, here, if we work it out, I think we'll see something like sorry, I've mutilated the position of that dot. We'll see 8 generators. You see 8 intersection points here. And again, the 4 intersection points that you're seeing here correspond to these 4 generators. And the intersection points here correspond to these, and the intersection points here correspond to these. Okay. All right, and here's this picture again, just to make sure I could draw it correctly. Okay, so another thing we could do is we could take Dane twists. All right, so if I take this knot in the solid torus, there's a diffeomorphism of the solid torus to itself that carries this knot to this one. Okay. As far as the action on H1 of the boundary is concerned, that's just a linear shear. Okay, so actually to find the invariant of the Dane twisted knot, we just apply that same linear shear to this picture here. Okay, so the invariant of this knot looks like this. And actually, if you think about it, these are oriented in opposite directions. Okay, another thing I could do is I could Dane fill the outside of the solid torus. That's like forgetting that curve A completely and just thinking about the knot as a knot in S3, right? So here, that would be like thinking about this trefoil knot. Okay. And so how do I do that over here? Well, I just Dane fill exactly the same way that I did for the case of a manifold with a single torus boundary and no sutures. That looks like pairing with these vertical curves. Okay, you see I have 3 intersection points. That's not an accident. Of course, that's the not-Floer homology of the trefoil. And so the thing to understand is that these 3 points line up. Right, here's the not-Floer homology of the trefoil. These 3 points line up. So for example, that this point here is this generator, and this point and this point are these 2 generators. And you can see, you can read off the Alexander grading of these generators up here. Okay. So say you wanted to compute the not-Floer homology of a satellite, where I take this 2-strand knot in the solid torus and glue it into the trefoil. Okay. I would do that by pairing this curve here with the invariant of the trefoil that we drew before. So what does that look like? Well, in that case, in this case, oops, let's draw this in blue so it's easier to see. I would do something like this. And here, do something like this. Okay. And so what do I see? I see I think 5 generators here, which are these 5 intersection points. And if you work out their Alexander gradings, you'll see actually that what we have is, maybe I'll draw these in 2 different colors, blue and red. So blue. Okay, and the so the blue and the red generators have opposite Z mod 2 gradings. Okay, you'll notice actually that, you know, if you're familiar with these things, this is the cable of the trefoil that Hedden discovered that has exactly the same not-Floer homology as the 3,4 torus knot. Right, so these 3 blue generators correspond to these 3, oops, that's intersections over here. Okay, so that's an example. You could ask, you know, when can we actually understand what this invariant is? Okay, so a very nice, you know, kind of the simplest situation that you can have is, we'll say, I don't know why I'm missing a G here. Okay, so we'll say that K is linear if little hfk is just a collection of line segments, okay, union of line segments. So that's what we saw for this knot back, not this knot, but, you know, the trefoil inside the solid torus. Okay, and I guess one thing we saw is that linearity is preserved under Dane twisting. It's kind of straightforward. So actually, you know, a lot of the most simple knots in the solid torus that you might consider are linear. Okay, so if the union of the knot and this braid axis is an alternating knot, and K, thought of as a knot in S3, is an L-space knot, then this Floer homology is linear, and it's determined by classical invariance. Okay, and that's basically the same theorem that says, like, that Link Floer homology of an alternating link is determined by classical invariance. Okay, so kind of a nice corollary of this. You know, I should have mentioned when I was talking about cabling, right? There's a long and really great history of people who have studied satellites, the not-Floer homology of satellites, starting with Eftekari and Hedden, including Jem Ham and Adam Levine. So there's a kind of story of Hanselman and Watson that uses these curve pictures, and also a story of Wenzhou Chen, which is, I think, related but not really the same as this, which also uses curve pictures. And yeah, so a nice thing that you can say is that if you take a linear knot and you use it as a pattern in a satellite, then there's, in some sense, a formula for what the knot Floer homology of the satellite is. And the sense in which there's a formula is that you can write it as a direct sum of different sutured Floer homologies of the companion knot with respect to different sutures. Okay, and that's just because these knots here with different slope, that, you know, pairing with those is giving you a sutured Floer homology. Okay. So for example, you know, here's a knot that you can compute for using this, which is this maser pattern. What's a knot that this kind of technique doesn't work on, or at least what's a knot that's not linear? Well, if I were to take the PQ torus knot inside the solid torus, and then use that as companion in some other knot, like maybe this one as pattern, then actually Hanselm and Watson's work that I'll talk about in a minute or two would tell you that, that you know, that knot is not linear, actually. Okay. So now let me finish by talking about two kind of generalizations of this thing. Okay, so one thing is that you could think about the differentials on knot Floer homology. Okay, and so for knot Floer homology of a knot in S3, we know what that means. We have a filtered chain complex and two different differentials on it, given by forgetting the base points. Okay. Now, in our situation, it's still true that if we go back and look at this twisted complex CFD hat of A, that's in some appropriate sense filtered by A. And maybe the appropriate sense is that, you know, you're adding in some more differentials to get CFD hat of S1 times S2. Okay, so for example, let's consider the core knot of the solid torus. Okay, so in CFD hat language, that would just correspond to a single generator here. Whereas over here, the invariant of the solid torus itself is this generator with a differential on it. This is a rho 1, 2. So you see, I've had to add in this extra differential. Okay, so what does that correspond to in this kind of a picture where we draw HFK? Well, in this simple case, it's kind of easy to describe. First, we have to, we lose the Alexander grading to some extent. So we have to think about this picture now on the cylinder rather than the plane. And then actually what happens is this just kind of pushes off. And that's one differential. And remember, there's a DZ and a DW on knot Floer homology. And the DW is the push off in the other direction. Okay? And the fact that you don't get the same thing, but rather the same curve translated by one is really a reflection of the fact, again, that this curve has winding number 1. Okay, so for example, if I were to take sort of the braid we were looking at before, whose invariant is these two arcs, what this push off looks like is something like this. Okay. And the other push off does kind of the opposite thing. So, and you'll notice that now they pull apart to give unknotted curves, but those are at height distance, a different distance 2 apart instead of 1. Okay. So for example, if you wanted to compute the differential of cables on the trefoil, well, what I could do is I could draw this same picture that I drew before, and I now have to kind of stretch it like this. So It's maybe gonna look like. Okay, and I'm a little bit short of time, so maybe I won't finish drawing this picture, but you can imagine that I count disks in this picture to get the differential. Okay. And the last thing that I wanted to talk about is the fact that we can also use this formalism to think about operators. Okay, so now I'm going to think about a manifold with two torus boundary components. And so in Lipschitz, Oswald, and Thurston world, that gives me a bimodule where I think about both boundary components as being bordered. And then I can glue that to my manifold with one torus boundary component and get a functor from the Fukaya category of the punctured torus to itself. Okay, and Hanselman and Watson gave a really beautiful description of this functor in the case when this manifold here is the cable space. Okay, but there are other interesting functors that you can consider. For example, there's what's called the net cutting operator. That's just T2 times I, where I just have a little suture disk on both sides. Okay, and you see if you glue this in, it has the effect of killing the sort of suturing, the sutures that you see for little HFK. So for example, what this functor does is it takes this arc and transforms it into a figure 8. Okay. Or another interesting functor that you can have is the functor where the manifold is the solid torus again. Okay, but now I take K is kind of a point, you know, this should have been, let me write this correctly. K is a knot in the middle of the solid torus. So it's just a knot lying on the central T2. So maybe it looks like S times S1 times a point times a half inside of here. Okay, so I could remove a neighborhood of that and suture it. Okay, and then when I apply this operator, what I'll see that it does is it just adds a sort of strand on the outside of my original knot. Okay, so that's the geometric action of this operator. Okay, and that's an interesting operator to consider, for example, in the Link homology. And so what does this operator do? Well, its action is a little bit more complicated, but not too much. So for example, what it does here is it takes this figure 8, and then I get 3 spin C structures. Okay, well, I mean, actually I get an integer's worth of spin C structures, but only 3 contain any curves. And the first one contains kind of a vertical figure 8 like this, and so does the conjugate symmetric spin C structure. And then in the middle, we see something quite interesting. We see this pair of arcs crossing to form an X. Whereas if we apply that same functor to this vertical curve here, then we get 2 spin C structures, and the action is like this. Okay. So for example, the kind of thing that you could do with this operator is, well, if I apply this a bunch of times, what I get is the kind of 0n torus link inside the torus. Now, if I wanted to compute, for example, the Link Floer homology of the NN torus link, I could just take the invariant here that I calculated for the 0n torus link and give it a Dane twist. Okay, so that's a easy exercise for this case here to see how you get the homology of the 2n torus link in this picture. and maybe a more interesting exercise in the general case. Okay, so I am just about out of time, I think, so I'm going to stop here.
Thanks. So are there any questions?
I have one. Can you comment on how much goes through when you do this same kind of construction for Kovanov? I mean, I remember that Watson and Coberters are version for which is very similar story for Kovanov, and in particular for these operators you mentioned at the end. Do they exist in this setting, and are they compatible in some sense?
Yeah. So okay. So I mean, I think obviously the situation for Kovanov homology is going to be quite a bit more complicated, is my guess. But I think, you know, it's really interesting to understand, for example, you know, for lots of simple knots, there's some interesting analogies between Kovanov homology and not Floer homology, or between Homfley homology and not Floer homology, and Homfley homology and Kovanov homology. So it would be really good, for example, to understand, I think, what this picture, just for, say, this two-strand link, or for the 2n torus knot inside of S1 times D2 is saying about Homfley homology, or sort of any of the other flavors of annular homology that you might consider. And I think, you know, particularly, I think it would be interesting to look for what this, you know, where this decomposition into these spin C structure sectors is appearing. I think that's an interesting question.
So we have a question online from Melissa Jen.
Hi, thanks. I guess I was going to ask something similar to that. I was just thinking about Claudia's paper. Is there a reasonable notion of sort of being able to handle satelliting in the Kovanov case using this? Like, I know that there's not really like a CFDA for gluing with torus boundary, and we only sort of have these like balls, but has there been any work towards satelliting using multicurves?
Towards satelliting using multicurves, I think the answer to that question is no. I think, you know, if you were to ask me, I would say that maybe, so for example, a place where we understand pretty well what this Dane twist does is in the Homfley homology of a braid inside the solid torus. So, you know, I think that, and maybe, you know, maybe I'm wrong, because there's also, you know, it'd be interesting to understand where Rosansky's invariant of a knot inside of S1 times S2 comes from in this picture. You know, you can certainly.
I was also thinking, so you're saying like a Dane twist is just shearing. Is there a reasonable notion of limiting?
Right. So again, I think the thing to be cautious of is that the categories that you encounter in Kovanov homology or in Homfley homology are apt to be more complicated than the categories that that you see here. We have a, you know, somehow in non-Floer homology, there's really quite a nice miracle that this category is really nice and easy to understand graphically, and it's not maybe so clear that it's going, you know, that that's going to be the case in either of these other situations. But, you know, there should, for example, be some sort of deformation, you might hope, from Homfley to not Floer homology, and be nice to understand what that is. I'm not sure if I really answered your question, but
it helps. Thank you.
There's another question online.
Okay, so I have actually two questions. The first is about satellites. So can you sort of give your formulas for computing the tau invariant for satellites? From your
Yeah,
picture?
so that's a great question. I think the answer is no, I don't know how to do that at that point, but that's something that I am hoping to do. And so the issue really is that you have to think about what are these differentials on the knot Floer homology of the knot in the solid torus really look like. Okay, and I think so. For example, if your pattern is a torus knot, so you're thinking about a cable, that's a case that was already considered by Hom, then it's very easy to understand what this deformation is. You can draw a picture like this one that I drew here, and then think about how tau works in that picture. But what's maybe more difficult is that in general, even if the knot is linear, you might expect that there could be several differentials appearing rather than just, somehow what we did here is we took a couple of chains and glued them up to form a loop by putting in some extra differentials, right? So like both this, both this and this piece correspond to chains. And then, I take those two chains and I insert some differentials that give me a loop. But in general, I might insert a lot of extra differentials, and I might then have to use Jonathan's calculus to figure out what's going on. And it's not clear to me whether that's easy to do in general or only in specific examples, is what I would say.
Okay, thanks. And the second question, if I may, so what happens if you take two patterns where you see these arc invariants and you glue those together?
Right, so then
do you get some wrapping around the ends of those curves, or?
Okay, so
yeah.
you want to try and pair little HFKs. Is that what you want to do? Yeah, that's I'll be honest and say that I try my hardest not to think about that.
Okay, fair enough.
Because somehow you'll notice that in all the kind of interesting examples that we computed here, we saw that we were pairing, we could get away basically with pairing a compact thing with a non-compact thing. And then actually, if you thought about it carefully, it didn't really matter like what that choice of arc was that we used to define little HFK. But like if you think about the, it's not the case, right? Somehow that the bordered Floer bimodule associated to taking that picture with bordering on both torus boundary components. It's not the case that doesn't depend on the arc. That really has to depend on the arc, because, for example, if you glue it up to itself, imagine taking T2 times I and having on the one hand, just point in T2 times I as your arc, and on the other hand, tying a trefoil knot into that. Right? When you glue it up, you get two quite different three manifolds with quite different Floer homologies, I think. So something interesting has to be going on there, but I can't really tell you what.
Okay, but what would be the expected sort of homology that you get?
Right. So the expected homology that you get. So what it would be is it would be the homology of the sutured manifold. Okay, where you've taken your two pieces, glued them together along the bordered parts, So now, for example, what you get is a manifold with two sutured, two torus boundary components, but I drilled a puncture between them. Okay, so the boundary is actually a genus 2 surface, and it's it's this sutured manifold with this sutures on the genus 2 surface. And then you can see, for example, that it's actually quite delicate to so for example, now it really matters how you glue those two things together, right? So for example, I could take the sutures and twist them along that arc neighborhood. And then I'm going to get a completely different sutured Floer homology, and that's going to correspond presumably to the fact that I'm kind of twisted. I have to think about how do I pair these arcs that end at this puncture, and I twist them along that boundary a certain amount and no further. But yeah, so that's an excellent question, but I don't know the answer.
Okay, thanks.
Okay, so if there are no more questions, let's thank the speaker again.